All right, so let's go ahead and get started. All right, so this is a practitioner's guide to writing std-Compatible views. So why this talk? Well, it comes down to this. If you want to write a view and all you care about is a view, period, full stop, it's actually very easy. If you want to write a view that is compatible with the stuff in std ranges, those views, it's not easy at all. There's a lot of kind of little niggling details that are not easy to come by. So let's say you have your view here. All you need to be a range, obviously, is a begin and end. So maybe you did that, and I'm alighting like a constructor and some data members, whatever this view takes to do its work. And maybe you derive from range's view interface, and what that gives you is a bunch of operations in terms of begin and end. Like if you're a random access range, you might have the index operator, for instance, added by view interface. And by the fact that you derive from view interface, you're now a view according to the concept checks in the standard. So if all you want to do is use it as a for loop, you're set. Like that's all you have to do. But as soon as you try to do anything outside of that, you run into problems. And I ran into problems, and these two guys took me to task. These are two committee members. These are two of the folks that are like, they're not C++ famous, but the committee wouldn't work without them, right? And both these guys, particularly Tim Song, helped me out a lot with the design. So I had this view that I was trying to standardize, and the first version of it was just not up to snuff. Tim said, why don't you fix this? I fixed that thing. Why don't you fix this other thing? I fixed it. We went back and forth many, many times. And in the process, I learned a whole bunch of things that even though I had, read a lot of views in the standard, I'd read a lot of that standardese. I even reviewed some of the stuff before it was standardized. I still didn't know a lot of the details he was telling me about. And it comes up sometimes in SG9, the ranges working group, or the ranges study group, that lots of people in that room bringing proposals, even people who sit in that room regularly, don't know a lot of these details. So I figured someone needed to come on. I figured someone needed to disseminate this information to the wider public. So that's why we're here. Okay. So some of these changes, or some of these details rather, are just conventions, right? And they're not strictly necessary, but this is the way that's done in the consistency of the work in the ranges namespace. However, there's other aspects that are absolutely essential. Things do not work if you don't take these certain steps. So first and foremost is piping, right? If you don't write your view the right way, then it's not pipeable with other views. There's also a mutable begin and end in pretty much every view. Why you need a mutable begin and end is not at all obvious. And you've had years or decades writing a constant begin and end on anything that doesn't mutate the state of the thing that you're calling it on. And yet here you have to have the mutable ones. We'll explain why when we get to that. All right, so let's start from first principles. Like, what is a view? And this is a quote from the standard. So from range.view, it says, the view concept specifies the requirements of a range type that has the semantic properties below, which make it suitable for use in constructing range adapter pipelines. So again, front and center is that pipeability. That's the common use syntax that people are expected to use when they're using ranges. And here's the actual view concept. So a view is a range and is also movable, like, important to remember that moves are just an optimization of copies. So it is movable or copyable essentially. And then also enable view is true. Now, if you derive from view interface, you get true from this. And there's also like a template variable you can specialize for your type that says, hey, I'm a view, okay? So you have to specifically opt into being a view. The API, the concept checks that would look at the elements of the API and different expressions in terms of your type can't tell from it that it's a view without enable view returning true. So furthermore, T models view only if T has an order one move construction and move assignment of an object type T is no more complex than destruction followed by move construction. And this one's kind of a weird one. If n copies and or moves are made of an object of type T that contains m elements, then those n objects have O n plus m destruction. Okay, a vector is not a view, but think of a view for a second. Think of a vector you've got and you move it n times. Every n minus one empty vector has to be destructed. The final vector has to be destructed. And when you destruct it, you also destruct its m elements, okay? So if you're able to move something in order one and then destruct it at the end, it meets this requirement. But if you think of std array, it doesn't do that. Because to a std array, I'm gonna have to destruct all m of the n-1 empty arrays, I have to destruct all n-1 times m of those. So it's an n times m destruction story, okay? So either T is not copy constructible or it has order 1 copy construction, okay? Yeah.
Just a quick question. You said order n plus n destructions. Wouldn't that just be n plus n? Why the order there? I'm just curious. Like,
Order of what?
For the destructions on that first stipulation. So it has have this many destructions.
Yeah, this many destructions of different objects. Okay. But some of the objects are the m elements. Yeah, but in some of the objects are the containing things themselves. Yep. Okay. So if you are copy constructible, and then you have this requirement that you be order 1 copyable, right, or copy constructible, and then either copyable is false or copy assignment of an object of type T is no more complex than destruction followed by copy construction. This is basically the same thing from the move version. Okay, this is all like everything I've been talking about before is from the standard, which is why I'm reading off of the slide directly. These are examples also directly from the standard. A range type that wraps a pair of iterators is an example of a view. A range type that holds its elements by shared putter and shares ownership with all of its copies. A range type that generates its elements on demand. And there's a counterexample here. A container such as a vector does not meet the semantic requirements of view since copying the container copies all the elements, which cannot be done in constant time, right? That's an order n operation, yeah.
So remind me, if owning view owns some container such a vector, it's still a view.
Don't get ahead. Don't get ahead.
That does not delete the copy constructor.
Yeah, it just deletes the copy.
Yeah, we're going to talk about exactly that. Yeah.
So okay. Just thinking back, would like an old copy on write string count as would that fulfill the requirements of view?
A copy on write string because it has order 1 and it has shared state. Maybe? That's
a weird thought.
That's a weird thought, but that could be. And if you have your own cow string implementation, it could very well, because if it's order 1 copyable and order 1 movable, then probably.
More generally, any shared view of a range could satisfy that as well.
Yeah. Okay. So the way to think of views is that they are a lightweight reference to an underlying range of things, okay? This is not right, but it's a very useful way to think of views, okay? There is a way in which it's not right that we're going to get to in a bit, but it's almost right. And even the place where it falls on its face a little bit, you can still kind of squint and pretend that the first statement is true. And so that's the right mental model to have for views, I think, okay? Okay. So at a high level of abstraction, you have 2 major pieces that are responsible for how views get their kind of work done. And the first is the view template itself. So let's call that X, and X would be something like repeat view or transform view, okay? And then you have the range adapter that constructs X's. So that would be something like repeat or transform that respectively constructs repeat views and transform views. And views are always constructed from other views with a couple of exceptions that we're going to get to, but you can think of that as a hard and fast rule except those couple of exceptions. You basically don't use those couple of exceptions directly in your code. So you can think of it as views are always constructed from other views. They are not constructed from iterator sentinel pairs, and they're not constructed from other things, non-view ranges or any other kind of random stuff you might think of. Now, this was the first thing that really surprised me. This was the first thing that I had violated before I had those rounds of emails with the folks from SG9, right? I had a view that was essentially constructed from an iterator sentinel pair, and that is not the way we do things. Okay.
So Zach, one way is if I have a view, I have to think, oh, this just came from somewhere else. This is a view, it's from something else.
Right. And so we're gonna get to how, as we just saw, a vector is explicitly not a view, and yet you can write v pipe, filter or something. How does that work? We're gonna get to how that works. All right. So here's an example view that I took from, basically this is transform view with the function f stripped off of it. Okay, just to keep things super simple. So it's a view that does something. The whole purpose of looking at this is we're gonna see what are all the major moving parts you have to have in a robust view versus that iterator only begin end thing we saw at the beginning, okay? So, oops, I'm going to get ahead of myself. Okay, so first we have the input range constraint on V. That could be random access range or whatever your requirement is for your particular view for the V that you are adapting. And then because rangeness is not enough, we also need to be a view. We have requires view there as well. Okay, and then the class itself is derived from view interface. This is one of many instances you're going to see where I'm putting view, input range, and view interface. They don't have the scope on them. It's just to make things fit better on slide, but those are all in std ranges, I believe. Then the private members are, we have a nested iterator template, we have a nested sentinel template, and then we have base. Base is an object of type V. And so you can see when we adapt a view, we actually take it by composition. We move the view that we're adapting in and hold it as a data member. The reason there's a template head on iterator and sentinel each is that, so think of like, any container would have like const iterator and iterator, right? So this is a way of expressing that because the iterators, const iterator and iterator are virtually identical except for one operation that they have distinct from each other. They're virtually identical except that one of them has like, const in a bunch of places and one doesn't. So you can make that an on-type template parameter and use that inside the implementation. We're going to see how that works in a bit too. So iterator of true is going to be a const iterator, and iterator of false is going to be a non-const iterator. All right, then we have default construction, and that is conditional on whether or not V is default initializable. Then we have construction from a base. We take it by value and we move that into the base underscore data member. And then we have these two member functions that get the base out. So the first one is going to return base by value, but only if V is copy constructible, right? And the other one is going to otherwise move out V, right? So we know V has to be movable or copyable because it's a view. So one of those two is going to work, and it's going to pick the right overload based on whether you've moved star this. Yeah.
And the functions are based just your convention, right? They're not like a required sort of name that a view must have.
So this is the convention that is used absolutely everywhere, but yeah, it's not a requirement. Like there's not a view that I know of that uses the base of the view it's got. Like it's going to return V, the object type V, it's going to return base in some place, but it's never going to do base like base paren, right? Like I don't think I've seen that code anywhere in views. I don't think that exists. So this is one of the conventions that's just really useful, but it's effectively optional for your case if you don't need to ever take the base out of your view, right? And this would obviously be used in some case like, you construct a view, you iterate over it, and then you want to take the base out of it and do something with that. Yeah.
Two questions. So first of all, for base, which is construct qualified, I assume here copy constructible also, imply this all from one like copy constructions.
Well, that's a semantic requirement of the concept of view. So that needs to be true if it's copy constructible, but it's not actually enforced or checked anywhere.
Yeah, I understand that this is semantical. And the second question is why Sentinel does have NTTP?
Why does this? Because Sentinel can be const or non-const. That's just the way, that's just one of the conventions, right? So typically Sentinel is a stateless thing that's cheap to copy and whatever, but you get the Sentinel, you get the data member for this Sentinel from basis Sentinel, and you don't know anything about that or what it does. So the const one and the mutable one might behave differently.
Okay.
So you have to have two versions.
Okay.
Okay, and then you have 6 different overloads of begin in a typical case. And in the case of transforms, you definitely do. So the first one's, the begin pair of begins is very straightforward, right? I'm just returning a mutable iterator for begin and a const iterator for begin const, right? Very straightforward. If you look at just the sentinel end and the sentinel end const, those are also straightforward, right? I return a sentinel that is mutable for the mutable end and a constant one for the constant end. But then we do something kind of odd with these other 2 overloads, right? The other 2 overloads are these ones that are constrained by common range. And the idea there is that I want to return not a sentinel to the end if I have a common range meaning the sentinel and iterator types are the same. I want to return an iterator specifically because the sentinel doesn't have much of an interface. It can basically just compare against an iterator, but the iterator has the full interface. You can increment, decrement, so on. So if I have a transform view that I'm making out of a view that is a common range, if I want to reverse it, it's really convenient to have an iterator at the end and not a sentinel at the end if I want to, iterate across that reversed range. Yeah.
Wait, so I thought you're not allowed to overload on return type. I mean, even though it's common,
There is no
have-
overload. There is no overload in return type here.
Well, it's
Which two look like that to you?
the end for both the sentinel and iterator return. The one that's not qualified and the one that is qualified.
Yeah. So this is if this concept
Right.
is satisfied, then this one gets called. Otherwise, this one gets called.
Right, but is it a case that
That's how,
yeah. Okay, I see. That's the overload.
Yeah.
Okay.
In order to be correct, the const begin and const end also need to be additionally constrained on range const v.
So we're going to get to that when we see a more full on version of it. I did cut out a lot of stuff here, but that's the next thing I was about to bring up. You'll notice that we have common range of const v versus common range of v in these two cases, right? And that's because, again, you can see like in the const case, we're returning something different than we do in the mutable case, right? And so because we're doing that, like we have to be able to like do different concept checks for these different things. So this might return a different result than this, okay? Similarly, we have constraints on the whole template, on the whole transform view in this case, about like, our ability to call f on an element of the range and all that kind of stuff. All those kind of constraints are spelled out in terms of our v that we're adapting and the function f that we're using to do the transformation. But those apply just to, let's say v and f, if those are the names of the template parameters. They don't apply to const v and const f. And again, we don't know that much about v and f, they're template parameters, so we could get a different answer for those. So what you're going to see in a lot of cases is not only are there differences between constraints on different members, but often the const members will have almost all the constraints from the template as a whole repeated, but with the const versions. We're going to see that later, but that's another thing that kind of surprised me when I first started working with this.
So, is iterator, if we were to write a concept for iterator, would it be a superset of the concept for sentinel?
No.
Not exactly. They're overlapping, but they're not perfect subset. Yeah.
Yeah, to expand on that, an iterator does not need to be comparable, but a sentinel needs to be comparable with an iterator.
Yes, that's right. Yeah.
And you might have just said it, but I'm a little slow here. So if I had a const view of a non-const v, which of these would it call if I asked for n? Wouldn't I
A
get
const view with a non-const v?
Yeah, the view itself is const, but
So
it's
v is a data member. So if the view is const, v is const as well.
no, but it's non-const. The view.
Are you talking about the template parameter?
Yeah.
The template parameter is always not CV it's never CV qualified.
Yeah. The CV quals get stripped off of the template parameter before you ever get to this.
Yeah,
point.
but your this is const. That's why your data member, or non-static data member is also const.
Yeah, it's deep const.
Yeah, because it's a non-reference data member, it has the same constants as the class. Yeah. Okay. So here's another thing that's kind of interesting. When I first started looking at the std views, I was like, why are we re-implementing something like size? So if you don't know, view interface gives you size. But the way that it gives it to you is view interface only knows about the iterator and sentinel. That's all. It doesn't know anything about like, oh, the thing they came from might have been a container of some kind. It doesn't know anything about that. So the way it implements size, it does std distance. So let's say here, our v that we've got inside is somewhere down inside of v, it's got a std list. Okay, at bottom, the thing that we're adapting, someone wrote, for their std list L, they wrote L bar transform view, okay? So at base, we've got a std list. So if we do the distance between the iterator and sentinel for std list, that's going to be a linear time operation, but std list has a size member that gives it to you in constant time, okay? So by calling ranges size on base, which ultimately just tries to use dot size or ranges size of base on whatever base's size implementation is, you drill all the way down and eventually you get to the list and then you say dot size on the list itself, right? Because that's what ranges size is going to do. And so then you have an order 1 implementation for this instead of order n. So sometimes there's going to be an implementation of something that comes from view interface that you can do better locally in some cases, so you re-implement it inside the view. Yeah.
Are you sure that it calls distance in the view interface? Because that doesn't seem right.
Yeah, I'm pretty certain. But I mean, whichever way, like if it's got a forward iterator or a bidirectional iterator, it can't do any better than the moral equivalent of distance.
But I think it just doesn't have size then.
No, I think it has a linear time size. Or, okay, so I could be wrong about that. It maybe doesn't have size because linear time. That actually might be true. I'd have to go look. I don't remember. But the point is, the point is the same, which is that now I can provide size and I can possibly provide it in O1, so I'm going to do that. Yeah. You had a question?
I was just trying to think out loud. Like if V is like a pair of input iterators, you're not going to have these because that's like not a size range.
A pair of input iterators is not going to meet the view requirements though.
Okay.
So, but if you had something that's implemented in terms of those, then yeah, at bottom, you would end up doing a linear time operation. That's right. Yeah.
Do you know why view interface doesn't just do this?
Because it can't, right? So it doesn't know, it doesn't have a base. It doesn't have a range to look at that it can call size on. It just has an iterator and sentinel, and that's it. Yeah.
Okay.
Okay, so there's a lot of moving parts there. So let's look at it. This is one slide you can refer back to later. So remember before with our very simple view, we just had begin and end, that's it. And that qualifies as a range, is usable in a range-based for loop and stuff, is gonna work for many use cases. But the full fat version has all these things. So we have the iterator sentinel types, or technically templates. We have the base underlying view, and we have those members to get base out of the view. We have a default constructor and then a construction from the view we're adapting. We have these different permutations that cover all the cases of const versus mutable and iterator versus sentinel overloads of begin and end. And then if it comes up that we know that we can beat the implementation in view interface or add an implementation that view interface can't do, then we might do that as well in our view. Okay. So this is what I'm talking about when I say that people don't widely know that these are all the kind of moving parts you want to have in a full-fledged view. So to give you some idea, so like there was a talk earlier this week that got a few of the details we're talking about here wrong, and I'm not casting any shade on him because I made all the same mistakes. Hanna Duskva's made all the same mistakes in her CTRE libraries of views. There are very good programmers who are making these mistakes. This stuff is not well known. That's the purpose of the talk. Did you have a...
Yeah, could you write size by using CRTP?
Could you write size?
You have the base function in your derived class?
Well, you could. And so the reason view interface doesn't, though, is because
it could provide a base implementation.
It does provide one, but based on the iterator types.
Right. So it's not allowed to look at the derived type and then use it as a whole. It only uses begin and end out of the derived type, and that's it.
Okay.
View interface, I'm saying. Yeah.
That's also why you need to provide rbegin and rend.
That's right. Okay, so like I said, there's another piece which is not the view itself, but the range adapter for that view. Okay, so now before I cut and pasted stuff out of the standard, and it was transform view, and to make it simpler, I got rid of F. But in the standard, they don't actually have any code for range adapters. They just say, it's a range adapter. So this is code out of GCC's implementation. So this is not the range adapter itself. This is a concept that's going to be used by the range adapter. So in GCC's implementation, for any view foo view, they have a can foo view concept like this. So this is very simple, as you can see. Like, it's a lot of words, but it's very simply just saying, can I construct a transform view from an object of type range and an object of type F? Okay, that's all it does. So with that in hand, we can write our range adapter like this. Now, again, it's a lot of stuff, so we're going to do it a piece at a time. So first of all, I've got the struct itself, and then I make an inline const expr1, and we call that transform. So that's the thing you're actually calling. It's a callable object, not a function when you use transform. So you say, v pipe transform, you're calling an operation on this. This is that call operation right here. And as you can see, it takes a range and an F, and then it just immediately returns a constructed transform view from that range and F. Very, very straightforward, okay? It's constant, it's const expr, it returns whatever this expression is, and we said no discard because if you're constructing a view, you don't want to write code that drops on the floor by mistake. And then we're going to constrain it by saying this expression needs to be well-formed. And the way I'd see if that's well-formed is with that concept that just did that expression on the previous slide. Looking up here, I'm kind of cheating. I took what GCC does and I removed it and I put this thing from Boost STL interfaces because that, you know, the one from GCC is like an implementation detail with like, you know, the wrong case so that it's not usable by mere mortals. But the idea is the adapter does this thing where like, you know, if you want to make a transform call to this, you can give it the range and F, right? But you never really do that. You put your range R bar transform of F, okay? There's no overload for that here. So this thing basically does a bind back on these arguments here, and then takes everything after R and puts them to the side. And then when it comes time to call this actual function, it applies those arguments that it had bound and then R, and then eventually calls this, right? So this is all the machinery to make that automagic. Yeah.
I think as of GCC 14, you can actually get that out of the standard library without having to spell it that way.
Yeah, so there is the closure type, but we need an adapter here, not the closure.
Okay.
And for some views, you use the closure. For some, you use the adapter. It just depends. And so, unfortunately, that's not a standard thing. This is the implementation of the thing that Barry put in that paper that introduced that and said, it might be nice to do this with adapters too. And so I just put that in STL interfaces. Yeah.
And by design, the adapter that does the bind back, it can't be SPNA friendly, right?
I couldn't tell you. I don't remember that detail. I'm
mean,
not
like
sure.
it has no way to know whether the F is acceptable until you reach the bar.
Oh, in that sense, yeah, absolutely. That's right. Yeah, because it's going to bind to those things and it hasn't seen R yet. So it doesn't know if R and F are compatible because it can't do this expression until much, much later. Yeah, that's right. Okay, so there's one part that I left out, which is viewable range here. Okay, so remember I said we always construct views from other views, right? And yet we've got this constraint here, viewable range. Yeah.
Can you please go to slide back just for a moment?
Mm-hmm.
But you don't have forwarding references here, right? So you always try
yeah, it's just
in this concept to construct transform view from R value always.
Not from an R value. No. This is becomes a forwarding reference because
because you instantiated
the category.
Basically?
Well, no. I mean, I'm saying if you put tref here, then we add ref here and it collapses. If you put tref here, we put ref here, it collapses a tref. Like the value category is deduced here, and then we just add ref here.
Okay,
and then,
so somehow value category deduced in the template branch.
Exactly.
Okay.
Yeah.
But usually what I would do is just requires this parents and range ref. No.
But this you need decal val here. You don't have something to cast. There's no value, so you can't do what you described.
If you did it in the parameter, you'd have to do stood forward inside anyway.
Yeah.
It's just verbose.
Mm-hmm.
Okay. So what does that viewable range do? So viewable range works like this. So viewable range says either R is a view, okay, that is one kind of thing that satisfies viewable range concept, or the other major case is that it is a range that is not a view, and then that case has two subcases, which is either that non-view range is an L value reference or it refers to an object that you can move, okay? So we didn't take advantage of any of those properties of a viewable range in the adapter, right? We didn't have like an if context for, well, if it's a view, construct the transform view this way. If it's a L value reference, constructed this way. We didn't do any of that stuff. This was the first major thing that I was like really perplexed by when I first started looking at this, right? Like, why aren't we doing that? This seems like essential thing that the range adapter has to do. Why is it called a range adapter? It's not adapting anything. It's just stupidly constructing this thing and returning it, right? So that happens elsewhere. Where it happens is there is a deduction guide for transform view that uses all T. We're going to get into that, what that is. But all T is the thing that handles that impedance mismatch. Either you're a view, in which case all T just says, fine, you're a view, I don't have to do anything. Or you're one of those two range cases and then it does something, and we're going to do what that something is. So this is what those deduction guides look like. Pretty much all the views have this deduction guide. The only ones that don't are the ones that are involved in doing all T itself. So what this deduction guide does is it says, you gave me a range. I'm going to maintain, which we don't usually do in deduction guides. I'm going to maintain the value category information here. And then I'm going to say the range we actually, or the view we actually construct is not from that range directly, but from whatever all t of that range returns. Okay, so that is how we get from a viewable range to an actual range. An actual view, I should say. Because either it's already a view and all t doesn't have to do anything, or all t does some adaptation. We'll get into what that adaptation is. There was a hand? No? Okay. So, all t. We're going to talk about all t. It's really nice to back up a bit before we discuss all t itself and talk about a couple of items that help with intuition for what all t is, why it works that way, and why views do things in terms of all t. So first we're going to talk about borrowability, and then we're going to talk about how the std ranges algorithms handle cases of value category, the differences between L values and R values and things like that. Okay, so first of all, borrowability. So borrowability is done in terms of borrowed range, right? So we have this borrowed range is a concept. There's a variable template called enable borrowed range that you can specialize for your range to say if it's borrowed or not. But what borrowed means is that if I've got my view and I say begin and end, I take those iterator and sentinel out, and then the view goes out of scope, have I invalidated the iterator and sentinel or not? Okay, so can they exist independently of the range that you took them from? So think of vector. If I have a vector and I take its begin and end, and the vector goes out of scope, obviously the begin and end now dangle, okay? So that means a vector is never borrowed under any circumstances. It's just not a thing. But span is kind of the opposite of that. Span already refers to some other extrinsic memory, right, that it's referring to. So if I take references to that reference, I get references to that extrinsic memory. If the span itself goes out of scope, the begin and end I got from the span are still fine, as long as the span was constructed properly and only the span goes out of scope and the underlying stuff is still there, okay? So some ranges additionally are conditionally borrowed, and usually the conditionality is based on whether or not V is borrowed itself. I should have maybe put views there. Some views are conditionally borrowed because that's the common case where we have the conditional thing. So if I have a transform view that's transforming essentially a vector under the covers, then that's probably not going to be borrowable. But if I'm doing the same thing on a span, it is, if that makes sense.
Transform views currently never borrowable.
Yes.
Oh, yeah. No. That's right.
There's a proposal for
This
that.
is your paper.
I wrote a paper about it. Yeah. So I'm gonna call altitude on that one, and I'm gonna say that normally I wouldn't make that mistake. But yeah, that's absolutely right. So pretend I said some other view. Yeah.
Take view.
Yeah, take
view, right?
I said take view. Take view. That's right. Okay. So here we have, now we're going to talk about the std ranges algorithm. So here we have a std ranges algorithm, transform. We've been talking about transform views, so why not talk about transform? So obviously it takes a range R that is going to do its work over. It's going to take an output iterator to put the result of the work. It's going to have the F that's actually going to do the transformation. We have a projection we don't really care about for our purposes. We also don't really care about the constraints on the function. What we really care about is this return type. Okay, so what the return type is, this alias, unary transform result, is an alias for in-out result. So all the std ranges algorithms that have this form where they take a range, they do some work on the range, and then they spit some output to the output iterator, they all return the last position in the input, the iterator to the last position in the input, and they return the final position of the output as well. Okay, that's what the in-out result gives you. So you would expect this to give us like that, right? Iterator T of R and O. But instead, it gives us a borrowed iterator T of R, okay? So what does that do? Well, the borrowed one denotes, and this is a quote directly from the standard, it denotes dangling if R is an R value and borrowed range of R is false, and otherwise it returns iterator T of R. So in other words, if you have something like this, where you have a vector which is never borrowed, and it's a temporary. Clearly, if I returned result and I had the .in member of the result was an iterator into that vector, I would have an immediately dangling vector. So instead, we put this value in there that's just called dangling, where it's of type dangling, right? The .in data member is of that type. So it still got the last position of the output in the output result. It still did all the work that it did in the transform. It's a function with side effects. We don't want to say, well, I can't return all the output, so I'm not going to do anything. We don't want to make it ill-formed, right? Because it's perfectly valid to do this operation and catch the output somewhere. But we just don't want people to be able to say .in is an iterator and I'm going to like compare it to another iterator or increment it or something like this, because now we're in UB land, okay? So this is done this way in the stood ranges algorithms because the algorithms only operate on the iterators and sentinels to the underlying ranges. They have no idea what the lifetimes are of the underlying ranges, right? They have no way to see that. I could have had a vector v in scope, and I could have written stood move of v there instead of this temporary vector. In that case, like it's actually safe to return .in, but it can't tell that. It cannot reason about the lifetime. It has to make these sort of safe guesses in terms of the R value or the value category where there's R value and L value, right? Okay. Yeah.
And for parallel range algorithms, we now have borrowed iteration for in and out because we take range as an output.
Right. Interesting. Okay, so the reason I said all that stuff is because views are different from this. So if you're used to that, to thinking about that in terms of the way stood ranges do things, views actually take the view that they adapt and they become a data member. So it knows the scope of that data member. It knows the lifetime data member because it's a data member, right? It's within its own lifetime for any particular view. So they don't have to do these kinds of things. So now what we need to do is we need to come up with some scheme whereby we can say, this thing is an R value or it's an L value. And if it's an R value and I don't know about its lifetime, I'm just going to move it and hold it and own it. Okay, that's something you can't do with the algorithms because the algorithms are just a function that runs and then you're done. This is an object you're creating and it can have a lifetime. It can own that storage of that temporary for its lifetime. Okay, so like I said in the previous slide, alt helps with this. And what alt is just an alias for calling views all on decal type of T. Okay, so views all is a function, or it's a range adapter, which is a callable. It's not really a function, but this is again for the standard. It denotes a range adapter object given a sub-expression E. The expression views all of E is expression equivalent to decay copy of E if the decayed type of E models view. So in other words, if you pass a view into all, it just forwards the view right back to you. Okay. Otherwise, if you can construct ref view from E, that's the expression that views all T is expression equivalent to. Otherwise, it's expression equivalent to owning view constructed from an E. Okay. And ref view and owning view are not mysterious. They do exactly what you think they do. Let's talk about it in a little bit of detail. But a ref view is just a reference to some other range. Okay. Everything in it is done in terms of that range. So like its begin is just calling the range and returning whatever its begin returns and so on. It is copyable and it is a borrowed range. Okay, because it's a reference, it's a lot more like span than like vector, right? So we know it's always itself borrowed, and you know it's borrowing the reference from whatever it refers to, and so it's always borrowed range. And so here's a little quick example of use. So if I have some vector vec on the stack, I can say ref view of vec twice, and then I can assign one of those ref views that I just made to the other one. That's all fine. Okay.
I think you can also say all, and it's going to be expression equivalent.
Yes.
Yeah, right. Sure. Yeah, I mean, so we're getting into, I mean, we already described what all does in terms of these. Now I'm defining what these do, but yeah, that's right. Okay. So owning view is also not very mysterious. It takes a range that is an R value and it just moves that R value into its internal storage, right? So it is move only and it's conditionally a borrowed range. So the typical use case is you get one of these things by calling all on something. And when you do that, the something is going to be something that's non-borrowed, but you could actually construct it from like, let's say a span, in which case it is itself borrowed as well. So think of vector, right? So if I have a vector in an owning view, the reason that vector is not a view is that it doesn't have O1 copy, right? But if you remember, the requirement was O1 move, or if it's copyable, O1 copy. But what owning view does is it disables the copy. And so now it's only O1 move. Okay. This is why I was saying before, if you squint hard enough it looks like a cheap to copy thing, but you have to move it instead of copy it. Okay, but it's the same idea. Now we have this lightweight thing that we can, put from place to place. We're doing it with a move instead of a copy, but it's the same idea as any other view that's like truly a pure reference. So even though this owns its storage and it owns like maybe 1 billion elements in an array, inside of a vector, we can still think of it as morally equivalent to a proper view that's just a span or something. And here's a quick example of use for this too. You make a couple of temporary vectors, you put them into a couple of owning views, and then I can't write ov1 equals ov2, but I can move ov2 into ov1. And then what happens is now ov1 contains that vector with 4, 5, 6 in it, and the other vector has presumably been deallocated. Yeah.
This is kind of an honest question, but on the previous slide, when you assigned the ref views to each other, what are you doing there? Are you changing? Like, if they pointed to different vectors, what would happen?
So this is a rebind, not an assign through, if that's what you're asking.
Okay.
Yeah. So as an aside, like all proper generic reference types should rebind and not assign through. Like it's categorically a mistake to ever make any reference type in a generic context assign through. There are a couple of talks about this at this conference in the past, but that's a very important point. Yeah, this is a rebind. Yeah. Okay.
One question.
Yep.
On the-
Oh no! Are you kidding me? All right. Okay, keep going.
While you're doing that,
You're going too fast.
is there any usage of? I'm sorry. I understand that borrowed range has the owning view is conditionally enabling borrowed range for correctness. Is there any usage of owning view that isn't a code smell where borrowed range is true?
Yeah, I don't know of one. I mean, I think the conditional borrowed range part is there just for like completeness and correctness in those odd cases.
Yeah.
But basically, like, I mean, my take is like I've never written ref view or owning view
Right.
explicitly, except as like some weird implementation detail in the guts of something.
Mhm.
But at a high level, you basically don't use them; you just use all.
Yeah.
So I think like it's probably a code smell unless it's an implementation detail.
Okay.
Yeah.
I think it's because it's user-facing API. Just as you said.
Yeah, exactly. So like you can use it in those cases. So you have to
Yeah,
define
and
what
it
happens.
should work just correctly. Yeah.
That's right. Yeah. Okay. So now, as we saw, there's a deduction guide on pretty much every view. And so since every view is using one of these all-T deduction guides, whenever you construct a view, you're always getting a view object that you're constructing that view from. Because if it was already a view, then all would just forward it through. If it wasn't already a view, it would either be turned into a ref view or turned into an owning view. Okay. All right, so now we're going to look at an extended example. So here I'm going to kind of like breeze by a lot of these operations. I do want to cover everything, but I want to breeze by a lot of them because they're pretty straightforward. I do want to call out the ones that are kind of odd because there's a number of them. So now we're going to return to the stuff we were looking at before, which was transform view with the F cut out of it. Now it's the full transform view. Okay. So obviously it's instead ranges. This template head says what we saw before, input range V needs to be satisfied, but also move constructible F because now we've got our function F back in scope. Again, we have to assert view V. And now we have a couple of constraints on F itself. So F has to be an object. And then regular invocable has to be true for this expression here. This is basically just saying like if I call F on some value that I got out of V, that needs to be a regular invocable function call, or F needs to be regular invocable in terms of that argument, that parameter list. And then we get this can reference thing, which honestly, I don't really know why can reference, the concept constraint is there. Does anybody know?
Void.
What's that?
Void.
Void. Is there more to that sentence?
Void. If the function returns void, then we can't.
Ah, thanks. Yeah, perfect. Yeah. So that's there on pretty much anything that's callable, and I guess that's the reason I understand now. So this is, sorry, not italicized, but this is an exposition only concept. So it should look like this. It's not actually can minus reference or something. Okay, and all can reference says is I can take a reference to it, which doesn't work for void.
And probably some other edge case.
Yeah. Okay, so now we get the private members, and the private members are mostly the stuff we saw before. We've got the iterator and sentinel nested templates. We've got our base V, and then we've got this movable box, again, not italicized, sorry about that, but movable box of F that we store the actual function f inside of, okay? And movable box is a little bit like optional. It's almost entirely like optional, but it differs a little bit. If you want to know the messy details, look at this part of the standard. But suffice to say, like for our purposes, you can think of it as an optional to a first approximation. Okay. Yeah.
Sorry, going back one slide. For transform view, why wouldn't f need to be as invocable?
It is.
It is. Yeah.
Oh, right.
So
Okay,
yeah, regular
sorry.
invocable.
Yeah, right.
Yeah.
Very
Regular
good.
invocable is the same as invocable, but with the additional semantic requirements.
Thank
Yeah.
you.
Okay. And so, excuse me. Now we've got some public members. We've got the default constructor, which just does the default thing, but it's conditioned on the default initializability of v and f. We have the constructor that we use the rest of the time, which takes v and an f, base and fun respectively, and then it moves those into the respective member variables. And then we have the two overloads that return the base. So again, not going to go over those because we already talked about them. Then we've got our begin and begin const. These are just the only overloads of begin. So the way we construct an iterator, we're going to get to the iterator definition a little bit later, but the way we construct an iterator is a reference to this view and then the begin out of the base. That gives us the begin iterator. The end iterator will do exactly this and just do ranges end. And then we've got the const one. And here we have all the stuff repeated, like I mentioned before. So the const one, because we have a constraint on the top that says range of v, well, it says input range of v, but that subsumes, range of v is subsumed by that. But we don't know if range of const v is true or not. So we have to repeat that here, okay? And similarly, we don't know if regular invocable is true for a constant f and a value out of the constant v. So we have to repeat that here as well. Okay. It is conceivable that you would construct everything with some view for which this just does not hold for whatever reason. Okay. There could be mutable overloads of begin and end, but not const ones, or that doesn't make any sense. But some difference between the const and non-const versions. Okay. So then we've got two versions of end. The one that, these are the two mutable versions of end, the one that returns a sentinel and the one that returns an iterator, because we have the requirement here of common range. So the sentinel just takes whatever the sentinel is out of base and then stores that inside of it, and that's it, right? And the other one does what we do with an iterator before. Like I said, we construct from a reference to this view, and then we take end out of here instead of begin, like we did it for the begin overload. All right, and these are basically exactly what we saw on the previous slide, except that again, we have to repeat all the constraints now with the consts in it, right? Okay. And then we have size that we already talked about before, same story as before, and that is the deduction guide. So that's it for the actual view. We're going to talk about the iterator and sentinel classes, but you can see it's already like a lot of code. And this is part of why like people tend to just kind of punt and say like, well, I don't really care about pipeability that much. I just want this quick and dirty thing I can run a for loop. Okay, so now let's talk about iterator. Like I said before, I did cut and paste this out of the standard. And so, they're defining iterator out of line. So the first part is just the template head repeated from the view, nothing to see there. Then we've got the template head for the iterator itself, which is just bool const is the only parameter there. And now we start to get into something a little bit interesting. The parent type is essentially the view that we were constructed from. And because we have that const parameter, we know that when we refer back to the view itself, we need to refer back to it as a const transform view of whatever type it is, instead of a mutable one. And we do the same thing for base. So maybe const is an exposition only alias that just does exactly what you would think it does, right? If this is true, then it's the const one. If it's not, it's the mutable one. And then we have, with the constness already formulated into how we define base, we say the iterator that we get from that base, whether it's const or not, that is our iterator type that we're going to have, and we have this default construction of it. And then whether it's a const parent or mutable parent, a back pointer of the parent is the other data member. Okay, so remember that the movable box that had the fun in it, right, in the view. We have to reach back through the parent pointer to get that function every single time we want to use it in this iterator. Okay. Okay, so now it starts to get hairy. Okay, the see below part is the hairy part. This is easy. Okay, so I'm going to get to the hairy part in a minute, but right here, all we have is like, an expression that boils down to like, when I call f on an element of base, like, what does that give me? Strip off the CV ref quals, and then that's the type for a value type, and then difference type is just whatever difference type the base used, okay? Now, let's talk about iterator concept. So iterator concept is defined like this. If base is a random access range, which, because of the hierarchy and subsumption in the concepts or ranges, that means that if it's random access range, it's either a random access range or a contiguous range. In either one of those cases, we're just going to call it random access now. Okay. By the way, this is also cut and pasted out of the standards. So this is directly from the standard. And then there's a bunch of otherwise, blah, blah, blah. Basically, it's saying if it's bidirectional, as a bidirectional range, then we use a bidirectional tag. If it's a forward range, we use a forward tag. And for input, and so basically for input, we use the input iterator tag, right? So very simple. All we did was collapse the contiguity down into random access, and everything else is just whatever kind of range we started with in V, that's the kind of iterator we've got here, okay? But then we come to iterator category. So if you don't remember this, iterator concept is the C++20 version of iterator category. So they have slightly different semantics because the rules for what can be what category of iterator in 17 versus 20 changed. So now we only define iterator category if base is at least a forward range. So if base is an input range, we don't even have an iterator category nested type def. Okay, that's funky, right? And the first time I saw this, I was like, why are we doing that? I still don't know why we do that. Does anybody know why we do that?
So it fails to compile?
It doesn't make any sense to me. I don't know why we do that, but there's reasons, right? This is one of the things that Tomasz, one of the two guys I mentioned at the top of the talk, he was like, no, you got to do it this funky way. Okay, so you have to before you have reflection from 26, you're going to have to do something like you have a base class, you specialize it, it's either empty or it's got this type def in it. It's really awkward to write. Okay. But then if we are in the forward range regime, not where we don't define this thing, the way we do it is like this. First of all, we say, if I took an iterator out of base, what does iterator traits tell me its category is? Okay? So we're going to call that C. Okay, so whatever that would be, we're going to call that C. So now, again, cut and paste from the standard. Do not look daggers at me anymore. Okay, so if what this is saying is if when I call f on an element of base, if what I get back is a language reference, then this whole thing is true, okay? So if calling f gives me a language reference, then if that C that we saw before, that's just the iterator category of base. If C models a contiguous iterator tag downgraded to random access, that's exactly what we did for the iterator concept. And then otherwise just use the same iterator category. So this part of it is mirrors what we did with the iterator concept very nicely. Okay, but if that thing at the top is false, we fall into the next page, which is it's just input iterator tag. Okay, and that's because the C++17 rules say that if you have an input iterator, if you have a proxy iterator, anything that doesn't return a language reference, then it must be input. It cannot be any higher category of iterator. Okay. Yeah.
I think I know why we do that funky.
We're going to learn.
My theory is because we only do this special case when the iterator category is only special when we don't return a reference, and then we downgrade it to input iterator. Mm-hmm. When the iterator concept would be input iterator tag to begin with, then we don't need to treat iterator category special in any way. And then when we ask the iterator traits for the iterator category, it might look at the iterator concept and give you the iterator concept, so it would be redundant.
That sounds plausible. Right. I like plausibility. We're going to go with plausibility equals true.
Yeah. The only thing weird about that is it's more effort to not provide the iterator category concept than
to just leave it there. Yeah. Okay. So I just want everyone to know, SG9 is the study group for ranges in the committee. He's the chair. I'm the vice chair. We don't have any goddamn clue Like that. Make of that what you will. Okay. Yeah.
I didn't fully follow what he just said, but if he didn't say it, I would like to point out that legacy forward iterator concept requires that the reference type is an L value.
I did not follow that.
Okay.
So maybe.
So the reason why the iterator category is only defined at least at forward, I think, is because of that additional requirement is checking is a language L value reference.
I don't see the connection between those two, but
Okay.
like, I mean, that's the thing. It feels like it's got to be related to that, but I don't understand how, because it feels like it's going the opposite direction. But anyway, I think that's the most realistic thing. But I agree, it's harder not to do it than to do it. But whatever. Okay.
Mhm.
All right. So now we can get into member functions. All that stuff was just, so when you actually write one of these, it's like quite a bit of painful metaprogramming just to write those two type defs. It's not a great story, right? Okay, but now we can get into the default constructor is, doing what you would expect. The constructor takes a reference to the parent, stores the address to the parent in parent underscore, and then moves current into current underscore. Now, if you don't know why we're moving an iterator when we usually just blindly copy them, it's because that's another change from cplusplus 20 iterator concepts, is that an input iterator can be move only. So you need to move iterators in many more cases just to be safe. Now, this is the only place that really differs between the const and non-const iterators. All this stuff is saying I can construct a const iterator from a mutable iterator. Okay, so part of the requirements is on const. And then I can be constructed from a non-const iterator, but because this must be true, I don't know, why didn't they just write false here? This seems abusive. But anyway, and as long as I can convert the v from base, then I'm good to do this move and copy the parent pointer. Okay, and so then once again, we have two ways of getting the base out, one for R value qualification, one for L value qualification. In this case, so note we have the typical case here, and then we have an exception that only works for const references because it's an exception to the general case, and we have two of them. They don't return both const ref. That's an inside thing for me because we've been arguing about this. But here, because you can't move the possibly input iterator out when you're just taking a look at it, you have to return a const reference to it. But here we just move it out. And again, we're doing a move because it might be an input iterator. If it's not an input iterator, the move is just going to be a copy. For a forward iterator or a random access iterator, it's probably just going to be a copy. Okay.
Is there a reason that that's a PR value instead of a R value reference?
I think, I mean, maybe not, but I mean, generally, like in the rest of the APIs, when we have a base that returns something by value and there's a move implied, we could have written an R value reference return, but we just moved instead. Okay. So for whatever reason, that's the convention. Okay, and so then operator star is, it's a lot of words again, but is ultimately pretty straightforward. We dereference current, we reach into parent, we get out fun. It's in a optional like thing, so we have to dereference that, and then we call invoke with that, right? So then we've got the first weird thing in the member functions themselves. So first we've got just regular increment, which does just what you would think it does. It does increment on the underlying thing and returns a reference to this. Then pretend that's not there. We've got the post increment, which also does exactly what you would think, makes it temporary, does the operation, returns it temporary. That only works for forward ranges, right? Because again, an input iterator rather, might be move only. So I can't return it by value here. So if you're an input iterator, because you came out of an input range, then you fall into this case over here. And in that case, we just do the operation and we just say like, yeah, I'm not going to do that. We just return void, right? It's a weird thing, but like you're going to see this a lot if you look at the views in std, because now the convention is post increment for anything that might include input iterators just should return void. Yeah.
Actually, the question about previous slide. So, but you don't need to, it doesn't matter. So basically, we always keep talking about this optional like thing, which is movable blocks. Is it empty only if we default construct iterator or like move from iterator?
Yeah, I think those are the two cases when it's typically empty. But again, I always forget and I always have to go look. So there's, it differs from optional in a couple of ways. So there might be some other cases where it can be empty. But yeah, it's an optional like, so it can be empty.
In the operator assignment, I think.
That could be. Yeah, I'd have to go look.
That's the point of movable box. But yeah, this is not the talk about movable box.
All right, and then now we're back into more familiar territory. So we have requirements that the underlying range is bidirectional, and then if we have, if that is true, then we just have decrement and post-decrement as you would normally have them. We also have plus equals and minus equals, again, only if we are dealing with the random access range. And then we have the index operator, again, only if we're dealing with the random access range. And then we have equality. So the equality, as you would imagine, just dispatches to whatever the underlying iterator's equality operation is and does that. There's a bunch of relational operators in Spaceship, but they do the moral equivalent of what you saw on the previous slide. They just dispatch to the underlying iterator and do that operation for those. Then we have some free functions, which we have is using the hidden friend idiom here. So we have addition of an iterator and a difference type or difference type and iterator, again, conditioned on random access range. And then similarly conditioned on random access range, we have a subtraction of an iterator, a difference type from an iterator or two iterators. Okay, and that's it. That's all the operations for the iterator type. Now we can look at Sentinel. Again, we repeat the template head from the view itself, and then the template head for the Sentinel. And then we do the same dance we did before. We use the const NTTP to tell whether or not parent and base should be const qualified or not. And then we take whatever Sentinel, whatever const qualifications is for that base, we take the Sentinel T from that, and that is our end type, right? So the Sentinel is constructed from a Sentinel of the underlying base, which usually means that, you could probably put no unique address in front of this and save a byte, right? It's almost always going to be an empty type. And then Sentinel is unconditionally default constructible because that's the property of Sentinels. It's also unconditionally copied here because it's another property of Sentinels. And we have the same dance where we can construct a const Sentinel from a mutable Sentinel, but not the other way around. And then when we have base, because Sentinels are always copyable, we just have one overload of it. And then the actual interesting operations are comparison with an iterator and subtraction if we have if we know we're a size Sentinel for the iterator that we pair with. There's also subtraction of Sentinel and iterator. I think the other way around. Is that right? That's just backwards. Yeah. It's the other sense of subtract, and then that's it. Okay. So we never saw in go ahead.
But the subtraction doesn't require random access of the iterator.
It requires size Sentinel 4,
and that's it.
Which may like one of the ways you can get that to be true is if it's a random access range.
No, it's not always true for random access range.
Well, a common random access range, right?
Common and random access dictate that it has to be sized.
Yeah.
And the
but the point is like that concept is doing all the lifting, right? So there are constraints on it. That concept is doing the right thing.
Yeah, but when you have the range over string literal, it's not common, right?
That's right. Yeah, because I mean, it depends on what your range is. There's no standard way of doing that, but the way you would usually do it is like a pointer at the beginning and then a null Sentinel, and then it's non-common. Yeah. Okay, so we did not see enable borrowed range anywhere. As was previously pointed out in the talk, transform view is unconditionally a non-borrowed range. And that is because you have the function f stored in the view. So if you were to take the iterator and Sentinel out of it, and the view goes out of scope, now there's no way for the iterator to do its work because now it's going through its parent pointer back to the view, which is something that's already outside of its lifetime. And so you're in UB land, okay? So there's no good reason why it couldn't actually be turned into a borrowed range for some cases, especially certain classes of F that have like no state, right? And there was actually a paper that me and Jonathan wrote that was trying to fix that, but the way it's specified is in such a way that it's never borrowed. Now, let's talk about borrowability. So borrowability, I think in general is a nice property to have, right? So if I have what do you call it? A span, and I take the begin and end out of the span. I can do all kinds of work. I can partially process whatever's in the span. I can take what I've got left over, put that in a subrange, and return that from the function. The span that I constructed could be a temporary within the function, or local to the function, I should say. And then the iterator and sentinel outlive it, and that's a really nice property. If in order to make sure that the thing I've taken the iterator and sentinel out of are always in their lifetime, I have to always pass it in as a parameter, so I know that it's within its lifetime if I return a subrange to that. So if I had something like a transform view that we just saw, if I made that transform view temporarily inside the function, I can never take a partial use of that transform view and put it in a subrange and then return it to the caller for further processing later on. I have to instead ask the caller to give me the transform view so that I know it's within its lifetime when I return that subrange that refers to part of the transform view. Okay, so that's kind of clunky, right? It would be nice if these views, which, semantically a view is like a reference to some range of stuff, okay? It'd be nice if that reference to some range of stuff, I could take other references to that range of stuff. Like I said, a partial processing of those elements in the form of a subrange with whatever's left and return that. That would be really nice. So I think it's just easier to reason about code when these types that want to be reference types are truly reference types, and we can treat them that way. But they have this kind of statefulness because often the view will have some state inside of it that the iterator needs. And so we have a lack of borrowability, and that's clunky. But that's not the whole story. But along those same lines, certain views just don't work with non-borrowed ranges because they know that there's this propensity for dangling, right? So for instance, if you try to construct a subrange straight from a range, that works unless the range is not borrowed. And then it says, well, I can't make this thing where I am advertising that I'm always a borrowed range. I can't make it from this non-borrowed range because that would be breaking one of my invariants. Okay, so that's just one example. Another example is that if you have a range that is an R value, like the example we saw before with a temporary vector, then ultimately you're going to wrap that in an owning view. Okay, and because you wrapped it in an owning view, that means that the borrowed range, that makes it not a borrowed range, and the result is a move only view. So again, at the highest level of abstraction, we want to think of views as these lightweight, easy to copy references of other things. But now I've got this thing that's a move only view. I can't treat it as a lightweight reference. It's move only. That's a little bit clunky. The fact that it's also owning its storage means that there's this impedance mismatch in my head between things that are truly only a reference to an underlying range of elements versus something that actually owns the storage itself, right? That's a little clunky too. So I prefer borrowability whenever we can get it. Yeah.
So Zach, you said that some views don't work with non-borrowed ranges. I wonder why some algorithms that do not work with borrowed ranges. I've never seen it that's constrained. One of the examples that comes in my mind is sort, for example. What's the point of calling sort on non-borrowed range?
Well, so I don't have a good answer for that, but sort copy does make sense on a non-borrowed range, right?
There is no sort copy, but yeah. There is no, there is partial sort copy. Yeah, but
partial sort copy?
Yeah.
Yeah, okay.
Sort copy, yes. I totally get it.
Right.
But
yeah.
Sort or
yeah, I agree, because you're doing an in-place copy.
Swap ranges on non-borrowed range, but on both non-borrowed range.
Yeah.
What's the point?
Yeah.
Okay, you wasted CPU time. Good.
Yeah, and I don't know why there's not that constraint there. I mean, I have. Yeah, I don't have a satisfying answer for that. I don't know. Yeah, that's a good question.
Generic code to know. Maybe possibly for generic code.
Yeah, I really don't know what the answer is, but okay. Sometimes borrowed ranges have dramatically better performance characteristics than non-borrowed ranges. So I did this experiment where I tried to take all of the std views that have state in their view and see how much of that state we could move into the iterator. And at least for, I forget which one it was, I forget which particular view, but it was dramatically faster. It was 4 or 5x faster. And the reason is that the iterator was able to do all its work using local data members. It didn't have to go back through this pointer off into space to some other memory location, read through that, and that dependent read was causing a lot of problems, especially for something where the actual unit of work was very small, like it was doing some very simple operation. But then there were other cases where the fact that you had to put all this extra information in the iterator made it bigger and harder to copy. It didn't fit in registers anymore. And so that actually was a pessimization. So it's not one-sided. Like borrowability tends to lead to better code, but it can definitely lead to worse code as well. So always measure. And in particular, this is what I was referring to before when I said it's not all one-sided, right? There's more to the story. And that more is that the space cost that I was referring to about taking stuff out of the view and putting it into the iterator can have some really peculiar space impacts. This is something instructive to look at. So let's say we have some R, whatever the range is, and we have view 1, view 2, view 3. Okay. So obviously, inside of if that whole view V is a borrowed range, then everything that you need to know to iterate has to be in the iterator, okay? Because if the view goes out of scope, the iterator is still good to use. If that is true, then if those are, let's say, filter views, okay? So a filter view, if you remember, like it goes till the next, whenever you increment, it goes to the next valid item, the next item for which the predicate is true. In order to do that, it needs to step until it finds an element. There might not be another element for which the predicate is true, so it needs to know where the end is, because when it's looking for the next element, it might reach the end before it finds it. So that would mean that the iterator has to have two iterators inside it, one for the current position, one for the end. For the iterator that it has, if it's a filter view piped 3 times, that is a filter view iterator, which itself has 2 iterators in it. And this end also has 2 iterators in it, potentially, if you have a common range, and that's what your filter view does, right? So you can get an exponential growth in the size of an iterator where it's exponential in the number of views you've chained together, okay? So that's the trade-off. If you're in that regime, it might be bad enough that that explosion of space is not worth any performance you might have gotten, and that explosion of space might eat away at the performance gains you could have gotten, yeah.
You'd also have the predicate in there too, right?
The predicate would also be in there, exactly, yeah. So the predicate is fortunately like, it is repeated, but like the predicate itself doesn't branch out into more storage, whereas the iterators do. So it's going to add to the growth only linearly, whereas the iterators will be exponential. Okay. Oh yeah, sorry, I already said that. All right. So one last thing I want to talk about, which is caching. So if you're designing one of these views yourself, right, you need to make some decisions about caching. So let's talk about non-propagating cache. So non-propagating cache is, again, pretty similar to an optional, but as the name suggests, when you copy it, the guts don't get copied, right? So the cache doesn't copy. So if you have a filter view and you call begin on it, it's going to cache that begin. If you copy the filter view and you call begin on it, it's going to have to compute the same begin again and then cache that. It didn't copy the cache over when you copied it. All right. And there's, in general, I think, a trade-off between performance and simplicity when it comes to caching. So again, with filter view, the way it works is because filter view needs to find the next available item whenever you increment it. When you get back begin from the filter view, you need to be able to dereference that right now. There is no increment step that happens, right? The first value of that iterator, what you get from begin, needs to be dereferenceable. Dereference operations have to be constant. That's part of the concept for iterators, okay? So you can't just say like, oh, well, inside operator star, I'm going to advance if I haven't advanced before or anything like that, because you'd be mutating state within your iterator. You can't do that if it's a constant iterator or a constant operation. So what you have to do then is the begin of the view actually does that increment step, finds the first valid element, or if there's no element that meets the predicate, it gives you end. And then that's what it returns to you. Because it did order n work, it's not going to try to do that again. It's going to cache that result, okay? So that means when you call filter view on the same range n times, and let's say nothing in the view, nothing in the underlying range matches the predicate, it's only going to do order n steps that first time constructed begin, and every other time it's just going to give you its begin, which is effectively the end of the underlying range, and everything's good, right? The problem with that is that if you, and this is one of the requirements on filter view, is that you're not allowed to change the underlying elements either while you're iterating through the filter view's view of the data, or if you do it outside of that. So let's say you iterate through all the elements that filter view gives you, and then you mutate some values, right? So the begin that it gave you, let's say it was pointing to element 5, and then you mutate element 3, and now it matches the predicate. When you iterate over filter view again, it says, here you go, here's element 5, that's where you should start. And it just completely skips over element 3. If you reconstructed the filter view, it would now point to element 3. If you copied it, it would also point to element 3 because it would have to redo the search for the first valid element. Okay. So this is something that Nico Yusudis has given a lot of talks about, and he has been really hammering on the fact that that is clunky. And I'm sorry, is that a question? Okay. He's been hammering on the fact that that's really clunky, and he thinks it's upsetting for users. I think what that misses, though, is that if you're iterating over the sequence of elements and you mutate them in place, it can have the same kind of problems. You can get into UB in either one of those conditions. But that is something that's true of any for loop that you write that mutates the thing you're looping over. We've all written that with a map, right? You look at a bunch of values in the map, you're like, oh, I don't like this one, delete it, and you've immediately invalidated your iterator, and boom, okay? So that kind of thing is already true. So all you give up by having the iterator cached is that between iterations, I can't also mutate the elements where I change the valid set of elements. And that's a pretty minor hiccup to me. I don't think that's something that you need to worry about that much. So what I'm saying is that if you didn't do the caching, then iterating over the whole filter view, mutating the elements, and then iterating over the whole filter view again would be less efficient, but would be correct. So there is definitely a tension between doing the caching and getting better performance in all cases, and doing the caching and getting, or not doing the caching and getting the correct answer, but less performance in all cases, okay? So that's just something to think about. However, I think also, also you need to think about the fact that filter view already exists, right? It's already out there in the wild. The reason we have to have those non-const begin and ends for everything is because filter view needs to be able to cooperate with these things. If you call filter views begin, it's going to try to call the mutable begin of whatever it's adapting. And if your view doesn't have the mutable version of it, it doesn't compile. Okay? So is that true? No, I got it backwards. But you know what I'm saying? Like if one of these mutable operations tries to call, or a const operation tries to call a mutable operation, it blows up. And then the reverse is problematic as well. So you already have this situation where people have to reason about iteration and caching. You've already got a situation where people have to have mutable begin and end. So because you want to make views that cooperate with the other views, that's part of the charm of them, they're composable. I think making a decision about that trade-off between performance and convenience, or performance and usability or whatever, you should make that decision in favor of what the standard already does, because you're already going to need to be interoperable with all the pieces in the standard as well. Okay, I said this as well. But one thing that I did leave out maybe the first time is, it's obvious you get UB if you mutate the elements as you're iterating over a filter view. What's maybe not as obvious is, in that example I just gave, like if you change element 3 and then iterate again, you get element 5 at the beginning, so you've skipped element 3. But there's actually other cases where you can get actual UB by changing the elements in between invocations of the iteration over filter view, right? So it is a hairy problem, and you do get UB in some cases. Yeah.
So the solution there is to be biased towards just creating anew each time.
Well, I think there's two ways to think of it. I mean, you could think of it that way. That's fair. But then what you've done is just essentially disable the caching all the time, right? And if you want to do that to be absolutely certain that things are safe, that's fine. But I think a better way to think of it is, I'm only going to use this filter view one time, so I'm only going to construct it one time if that's all I need. If I know I need to use it twice, then I also need to know that I can't mutate the elements in between in such a way that it changes their result of the predicate, right? And so if you put those two things together, I think that's also a way to think of it, and then you don't lose the possibility for the performance. Yeah.
Is there any room to add a way to reset the cache or throw away?
Yeah, the way to reset it is you just reconstruct the view, or you can also just copy it, either one of those is going to reset the cache effectively by starting from nothing or not propagating the cache because of the way the cache is stored.
I just wanted to make a comment. The caching isn't just a performance optimization, but it's also to satisfy the semantic requirement of begin on a view, which has to be one amortized constant.
Yeah, that's fair. So like if you don't do it with caching, then you have to do some hack like I'm going to say that the internal state is mutable, and then in my constant operator star, I'm going to mutate that state, and that's just unsatisfying because constant operation shouldn't be mutating state. Like, and in fact, the reason you cannot do that in the standard is that we make a guarantee that if you see const on a member function, then that's like it's safe to call that across threads. We're not going to touch any state. No state would be mutated, right?
Have to be in the constructor.
What would have to be? Oh yeah, you would probably do it in the constructor. That's right. Okay, and I think that's it. Questions?
You got 10 minutes.
Yeah.
I was going to redirect his question earlier about algorithms like sort accepting a non-borrowed range.
Mhm.
I think the use case for that is you have a generic template function that takes a range in. You might want to sort and then do a binary search on that range. And yeah, when you return, you're going to throw away all of it, but you are actually getting something out of that sort on that non-borrowed range.
That's
Yeah.
what I
What do
meant
you
when I
get?
said generic.
The range is now sorted, so then you can pass the range into another function inside that same scope before the non-borrowed range goes out.
So the idea is you pass in a range, is not a borrowed range. You sort that range because you pass it into the function you're in. Its lifetime is the lifetime of the function. So anything you do inside there, including sorting, including taking the result of the sort and giving it to someone else,
No, it's borrowed because now it has a reference. It has a name.
Mhm.
It's a value reference if it's in the
that
function.
doesn't a range doesn't become borrowed because you pass it to a function. That's not how it works.
But
He's saying that
it
if
has a name.
you're in the body of a function
Yes.
where it's borrowed outside, but you pass it to sort, if you're moving it into sort, then there's no way to access it after that point in the function control flow. But if you pass it as just name, that's an L value reference.
Yes, and it's borrowed. That's the definition of borrowed range. It's basically it's either L value or enabled borrowed.
L value or enabled borrowed.
Yep, and it becomes borrowed because it's L value reference.
Yes.
Yes,
I don't think that's true.
that's true.
That's true.
All L
Wait.
values are borrowed ranges.
Yes,
all right, because then you wrap them in a ref view.
Yeah.
Yeah, that makes
Yep.
sense. Okay.
Yep.
Yeah, got it.
So your example doesn't make sense.
Okay. Yeah. All right. Yeah.
Me?
Yeah.
Yeah, on slide 38 or 36, I think it was, you had a bunch of requirements on a member function, and I just wanted to make sure I was not misunderstanding the requirements of the member function.
Is this the one?
No, try 38.
That was 38.
That was 38.
That was 38.
Well, 36 then. Sorry, it's hard to see the numbers. No, you in one place you have like requires range and something, and then it requires some property of the range reference. And my understanding is that you don't need to require it's a range because wouldn't range reference only be evaluatable on ranges, or am I wrong in that?
Yeah, range reference only applies to ranges. That's true.
Right. So you require range and then something about the range reference. You've required ranges twice, right?
The reason it's done is because you get better diagnostic in the error if you explicitly do that before the type or the type trait.
Okay.
But also this is just an alias for like, tell me what decal type of star IT is, right? I mean that's all it does. And the IT, instead of like, you do reference T on an iterator and it returns a value, but then if you got a range, it does like dot begin first and then essentially calls reference T on that, right?
Yeah.
Or evaluates reference T on that.
Yeah, I just want to make sure I didn't miss the fact that like you can only do range reference T on ranges.
The type trait's already constrained on that.
Yeah. Okay.
Yeah. Well, is it constrained?
Yes.
Is it actually constrained? Okay. All right. That's news to me. I don't remember it's constrained, but yeah. So if you get better error messages, that's definitely a reason. But the other reason is just like easier to write it this way because you've already got the view and you know that it's a range. Yeah.
There's also the short thing of concept, so you might want to break earlier and not start to go down into the evaluation of the concept.
Given that roughly half of your presentation is about the complexity of dealing with const qualification, What's your opinion on the proposal that deprecates const qualified begin and end on views?
Oh, I mean, I don't know how you get rid of them, right? I mean, well, because the way you could get rid of them is everything's mutable,
Right.
right? Which is fine, I guess, because we have to support the mutable case. And it certainly makes it a lot easier to write the code. So, I mean, I don't know of any countervailing arguments against it. It sounds like a pretty good idea to me, but yeah, I think Rob was first.
Yeah, I mean, I have a list here of questions, but I'm going to pick up for you.
You want to let one person with one question go first.
Is this like shopping?
I don't like the fact that transform view is not borrowed, and I know that you have a paper and you said like you guys wrote it together.
Multiple
so
papers that went down in flames. By the way. Yeah.
So basically, you try to fix like more than just transform view, but let's stick to transform view. Basically, I'm not sure if you guys found the way to fix it without the API breaking change, but let's say that if it's not going to land the way you want to fix the existing one, is there a chance we're going to end up with having like 2 transform views?
So that was actually something that Tomasz mentioned when we were talking about the fact that I was using transform view in that view that I mentioned before that I was proposing. And because it was non-borrowed, but because like the view I was proposing had every reason to be borrowed, I said like, well, I'm going to make this other thing that's like transform view. It was called like
project view.
Thank you. Project view is what I called it. Right. Mm-hmm. And then immediately people were like, so we have a transform view and a transform view, but like nice. Like this is ridiculous. We can't have this. Go fix transform view. And then everyone hated all the fixes transform view. So I don't know the answer to that. I would not be opposed to having both those things in there, but I think it's sad that we have to have both of them.
Yeah. Another thing for the future, like I'm not sure what you guys think about that, but we might think that there are benefits for view to be both borrowed and non-borrowed for like deep performance case. You showed it, like borrowed also has a price, right?
Do you mean conditionally borrowed or like not borrowed and not borrowed at the same time?
I mean, yeah, like transform view and let's say projected view, like two views. One of them is borrowed, another one is
I
not,
see.
Like
Okay.
to enable different use cases. It might be for the future a good idea to have a template parameter to just explicitly for the users say what they want.
Yeah, maybe that would also be an API break, so you couldn't do it to transfer.
No, you can do it for the new ads, and I said for the future, for the.
I see. So you have like
the common views to the.
You have an alias that dispatches to one of the two. Yeah, that makes sense. Yeah. Okay.
I mean, the provision I had to write passed SG9, so.
What?
View. Yeah.
Did it?
Yeah, we voted to vote.
I was asleep then. I don't know. Okay, Robert.
Yeah. So pick up what Patrick said. I think the flip side of deprecating const is not paying attention to whether or not the thing is const. We can just use deducing this, right? And if begin and end are well formed, they're well formed, and if they're not, they're not.
Constraints on that would be ridiculous.
Yeah, then you have to write the constraints.
You can apply begin to forward like the range of yourself.
Well, I mean, I think you have to repeat all the basically you'd repeat the concept checks that we saw repeated. You'd repeat them that one time, but you still repeat them because you still have to check like.
But you can just write one overload for each one, right? Or one overload. Right, and then it's
sure, but that one overload has all the cruft in it that we're trying to get rid of. I think.
Are we trying to get rid of the cruft or the fact that we have like this second thing?
I think we're trying to get rid of.
Because then, I mean, the advantage of using deducing this is we'd solve the very important problem of the fact none of this works with volatile qualified views.
Yeah, man. Yeah, let's not talk about volatile qualified views, please. So I think. Totally derailed me.
Why not?
And now we have an embedded guy. See, you've agitated the embeddeds. What are you doing? So I think what we would like to do is just have the mutable only one so that this stuff drops away. But if you had the deducing this version, you would have to do this, and you'd have to say like, is this const? And then put that, like you'd have to have like a maybe const v with the constants of this somehow in it. Like
it wouldn't be a maybe const, right? You just use forward like and decl val.
Forward like what are you forwarding? You'd have like forward like of decl val
inside of you.
I mean, that's sure.
Right, so you'd say like stood forward like self of decl val v.
Yeah, I get it now. And those are equivalent, but it's just either way it's clunky to write.
My first question. You can see it has range and regular invocable, and then inside of regular invocable range reference t. So if you get rid of range, it still fails to be satisfied in the same set of situations, right? Because the range reference t will fail to evaluate to a type if v const v is in a range, which will then just cause the requires expression to be false.
Yeah, I mean, if this is constrained, like Patrick is saying, and I have no reason to disbelieve that, but then I think that's true. But I think also, like he was saying, you probably get better error messages this way. Yeah. So, all right. Any other questions? Yeah.
Yeah, so the paper we wrote about making transform conditionally borrowed is at LWG's.
I did not even remember. I just remember arguing with Tim Song so much that I thought I thought it failed.
Tim Song voted strongly against
Yeah,
it.
well, I know. Yeah, you didn't have to tell me that part. Okay, well that's good. All right, so there's hope.
That means you're going to have a hard time in library working.
Yeah, sure. Yeah. It's yeah, right. Yeah. Okay. Anything else? Oh yeah, Eddie.
On the subject of transform view 26, I hope it gets through loop because my current revision of UTF-2 depends on it. So
Yeah, exactly. I mean, like I said, it was motivated by the stuff that I was working on that now Eddie has picked up the work on. So yeah, it's very useful stuff. Yeah.
right, yeah, 29, yeah.
All right. I think that's it then. Thanks everybody.